Yeah, I will talk about large language models in 2023. Why do we need that suffix in 2023? What we call large is misleading in that large models of today will be small models only in a few years. Along with that change in the perception of scale, many insights, observations, and conclusions we make along the way with the current large language models will be outdated and in some cases invalidated. Fortunately, insights based on first principles or that are fundamental tend to stay relatively longer than the advanced ideas that look so fancy. In this talk, I would like to share such fundamental ideas that I have observed working in the field for the past 4 years, and mostly by observing some of the brightest minds that I'm fortunate to have interacted with. My hope is that whatever I talk about today is fundamental enough that it stays relevant at least for a few years. Let's get started. There's one unique aspect of large language models, and that is some abilities only emerge at certain scale. And this makes really important to just have a different perspective in viewing all this field. So here's what I mean. Details don't matter here. X-axis is some scale. You can think of it as a model parameter count, training data, training compute, whatever. You just think about some scale. Y-axis is also not that important. Some performance metrics of the task that you care about. And we have seen over and over this kind of pattern where small models just don't have any chance of solving it, 0% or random guessing. And at some scale, suddenly the model solves this task and sometimes very well. And this kind of phenomenon, we call it an emergence, a phase change like sudden emergence of this capability. And this is very unique for this large language models. And I think this brings many important perspectives change that for AI researchers. First one is this perspective of yet. So let's say we have this new idea that I want to test out. And let's say some kind of a new reasoning techniques, and I try out the experiment and say it doesn't work. Most of the time it doesn't work. Then instead of saying this doesn't work forever, I want to say this doesn't work yet. And this is really a fundamental change in the viewpoint. I'm saying this might not work for the current generation of the models, but in 3 years, 5 years, that might not work. That might just work. And so we should really not conclude many things that in a permanent sense. And if we think about why this perspective is not so obvious, we're so used to operating in an environment where the underlying axioms don't really change. So let's think about this, an experiment, an example where, let's say you run some physics experiment or you study thermodynamics, which I did, and then you run some experiments. And then if you have some new idea and this experiment doesn't work out, then you know that if you run it again 3 years later, this will not work. For that matter, 30 years later, this doesn't work. The underlying physics, second law of thermodynamics doesn't change. And we know this, and we're very used to this kind of situation. And a lot of the human experience is like this. So for the language models, what is the equivalent concept of such axioms underlying the field? And that's more like the most capable model at the time. And if anything, this changes. So say GPT-4 came out and then researchers built on top of it, a lot of research experiments, intuitions built on top of it. And then later on, some better model comes out, then many of these ideas are outdated, in many cases contradictory. And it's really important to think about this. And this calls for the need to constantly unlearn the intuitions based on such invalidated ideas. And this is somewhat a new concept that I rarely see people practice. And I think this is, we have seen this very competitive field of AI. There are many cases where people with 1 or 2 years of experience come in and have very impactful ideas and work done. And I think some of that has to do with this newcomers just come in with the fresh perspective and then try out the ideas that experienced people have tried in the past that did not work with the model at the time. Now it suddenly works. This, I think, is a very neutralizing force. And for people experienced in the field, I think this is something to think about. Another perspective I would like to talk about is we should go ahead of the scaling curve. So here's what I mean. When I work on this day-to-day research, here's kind of the mental picture I have. Document all the experiments that fail and because of this insufficient intelligence. So this is a very vague term, but maybe it doesn't just have enough reasoning capability to solve this hard math problem or coding problem. Then I kind of just document it somewhere and do not declare failure yet and make it easy to rerun in the future. And as soon as the new, better model comes out, rerun them, and then learn what works and what doesn't. And with this, I update my intuition, unlearn necessary stuff, and really build the intuition around emergent abilities associated with the scale. I think this will become more and more important. So here's a visual way of thinking about this. Let's, again, very simplified, not all of the tasks work like this, but the scale is just whatever, just some scale. And then I just put GPT-3 and 4 for the illustration purposes of two models at different scale. And let's think about this graph on the left, ability 1, some ability. And this one, GPT-4 cannot do it yet, but it's very close to the inflection point that a little bit better model, then we will probably suddenly will see this jump. And then the ability in the middle, we have even this powerful GPT-4 model is so far away from it that any kind of like approach is probably not going to work in a meaningful sense. And ability 3 on the right, this is GPT-3 is even past the inflection point. And at this point, whatever I work on will probably be incremental changes. And that is kind of the implication. In reality, I cannot think of whatever problem that I'm solving falls under one or two, but just having this mental framework and always thinking about it and going back to the previous slide, updating my intuition really makes it easier to pin down which problem I'm solving. So that's kind of the perspective I want to introduce. So the summary is that everything we do has to do with scale, and scale first perspective is really critical. But how do we actually build the scaling? How do the scaling done in the field? So in the next 20 minutes or so, I'll think about this problem. And so far, all the large language models use this transformer architecture. You probably have seen this plot many, many times. The details don't really matter. For us, this talk, we will think about the fundamental ideas and then build up from first principles. And for that, we need to aggressively abstract out unnecessary details. For that, I would like to say the internals of the transformers don't really matter as much. And so we are going to take this functional viewpoint of the transformer and just think about it as a sequence-to-sequence mapping with a bunch of matrix multiplications with the following array transformation. The input is a sequence with batch D model, which is kind of the width of the transformer, and length, the sequence length. And the output is same size array, and this is for training. For inference, it's different, but scaling happens at pre-training time, and this is the same length. So that's going to be the picture of the transform. Very simple sequence-to-sequence mapping. So let me illustrate with this functional viewpoint, input and the output shapes what happens from the beginning. So typically we have this sentence like this. I just took a random example. Many words don't map to one token, : indivisible. This is a string, so the shape of that is just string. And then the first step is to tokenize it. And then tokenization is done with some BPE or sentence piece, which is essentially an external model that try to compress the text as much as possible. So here we get the integer list. So now the shape is length. And then now we embed it into this hidden space, which we used to call word embedding. Now the representation of each token is its vector of size D model, and we have length of them. So shape is D model by length. And this is where actual computation happens. We have n transformer layers. And like I said, this is just a mapping from the same sequence to sequence. And here, everything is about scale, and scale really needs to be have as little assumption as possible. Here, what we want is each sequence token wants to interact with other tokens in the sequence. So we should just let them do it, but not get in the way of how they do it. So the one way of doing this in transformer is just just let them able to take the dot product. That's it, and everything else is kind of details, and model learns to do which one to take the dot product and so on. So this is where major computation happens, and because it's a high dimensional array, we're talking about matrix multiplication or array computation. So at the end of this transformer, we get the sequence, and then we just take this loss function, which I'll cover in the later section. This is just a maximum likelihood based on next token prediction. So just predict the next token. And we get a single number. Now we do the backprop and update all the parameters and so on. In practice, we do it in batch, which only means we just have this batch dimension prepended at the shape. The only interdependence across the batch is at the end, when we take the loss, we take the average of that. That's all the process. And like I said, this is where vast majority of the compute is happening. And so when we say scaling the transformer, this is where we're scaling, and we need to understand this part in depth. So let's do that. From first principle, scaling transformer means doing that part very well, which means efficiently doing matmulls with many, many machines. And this involves distributing or allocating all these matrices involved in the transformers to various machines. Which machine gets which part of the matrix, and so on. That allocation is the critical part, and we should do that while minimizing the communication between the machines. So this is the scaling perspective at the very low level. So that means we should think about this matrix multiplication. So I'm going to talk about this trivial matrix multiplication. Probably everyone knows how to do, but with the twist that we are using multiple machines and do it in a very scalable manner. We're going to scale it up to transformers later. So one at a time. So now let's say we have some 8 machines. There might be CPUs or GPUs. Now the first, and then we're going to do this trivial A, B equals to C, 16 by 16 matrix multiplication. And for that, the first step is to think about some kind of abstraction over hardware. These 8 GPUs or CPUs might be in the same room or same cluster, or maybe in different rooms or different buildings, whatever. We don't want to deal with such things. We define this mesh, which is like 2x4 grid, and then this layout is in virtual space. We don't care what the physical layout is. And that's, we call this, label this x-axis, and then y-axis for this hardware mesh. And then the job is for every arrays involved in this computation, we map this array axis to the hardware axis. That's what we're going to do. And so here I use little color notation where this first row dimension of A is a red 16y, means this dimension is mapped to y, and then yellow x means that dimension is mapped to x. So because there are 2 machines across y axis and 4 machines across x axis, what that means is the column, these rows are split into 2 ways, columns are 4 ways. So that's what I have this labels, machine 1, 2, 3, 4, and so on. This is the allocation for the matrices. Now let's think about what machine 1 does. And it has to do, if you look at the C, the output matrix, we want to specify that after this matrix multiplication, we want the machine 1 to have this slice on the top left corner of 8x4. So that's a requirement. And then we see what it needs to do. So it has to do, if you think about this matrix multiplication, we do like column-wise and row-wise. And so it has to get some data. It doesn't have everything it needs to do this computation. So we do that with this all gather operation, which is one of the MPI operations. And we will look at this. So communicate with the 4 machines. So 1, 2, 3, 4, each having their local data. And then after, like, it talks to 2, 3, and 4, gets the data, and it has all the copies. And all of them does the same thing, which is why it's all gather instead of just gather. And that's the process that happens. After this, machine 1 has all the copies it needs to do that computation. And that's what happens. And crucially, this part is done in parallel across all 8 machines. And that's where the speed up comes up. And then the cost was that the communication has to happen. So that's kind of the trade-off between the two. We have to think about the speed up being larger than the communication cost. So that's the matrix multiplication. Let's generalize a little bit. mapmol we can generalize to einsum, Einstein summation notation, which is just a higher level view of this array computation. So the two rules are if the letter appears in both input, multiply component-wise. I'll show you this. So if you look at the first one, numpy einsum of I comma I becomes I. So we have both letter I appears in the input. That means we just multiply component-wise to get I. So this is equivalent to A times B in NumPy. And then if the letter doesn't appear on the output, then sum over that dimension, I comma I becoming nothing. So we should do that component-wise multiplication and then sum it over. And if the letter appears, and the third one is ij comma j going to I. So what we do is just take the dot product over j, and then you get this comma. So that's the matrix vector multiplication, if you will. So that's the view of einsum. It can add many more dimensions. It doesn't have to be 2 or 1, it can be as many dimensions as possible. So now matrix multiplication from this perspective can be expressed as einsum of mn comma mp, with m being this contracting dimension. We take the product, sum it over to get mp of AEB. So that's that. Why are we doing this? We go back to this matrix multiplication example with this einsum. So I put it here. And then now, because we all have labels for these array axes, MP, MN, whatever. So now this mapping means that I'm just saying N is array axis mapped to Y order axis and mapped to X axis. And let's think about this, some magic decorator parallelize that has this mapping and does it for you. And I'm going to talk about how this might be actually implemented later, but the real implementation of some kind actually looks like this. So very similar to this. And we'll just think about it as a magic. So what it does is it inserts it all gathers in 2 dimensions and gives you back the parallelized version of this. So that's that. So einsum really exposes what we need to do. So yeah, now generalize one more thing. We were doing mapmols, but we are interested in transformers. So the most complicated operation happening is the self-attention layer in the transformer, which can be represented in einsums. Everything except for the softmax can be expressed in einsum. So we don't have to go into details, but you can lay out like just cleanly like this, and you have some inputs, X being this sequence of 3-dimension batch demodeled by length, and then all these are model parameters that are learned and will be updated. So when you have this, you have a bunch of einsum operations with labeled array axes. Now, let's go to just parallelization of this thing. So we have 8 machines. Now, instead of calling it X or Y, by convention, we call it data and model. And that is data parallel dimension and model parallel dimension. We're doing both data and model parallelism. And this is kind of the mesh TensorFlow way, old in like 2018. But now it's a little bit more general, but we still use this terminology. So changing this code, very little change. We just put this parallelize and just put B is mapped to data because B is like the batch dimension. We split across the machines in the data axis. And N is the sequence length. We never, in any transformer parallel version, we never parallelize across the sequence length because there are so many like things happening there. And D, nothing, H, the number of heads is the model. Actually, this is why multi-head attention, the inventor is Noam Shazier, and he actually likes really parallelizing stuff. And so how can we parallelize this attention mechanism? If we split it into very separate heads, then you can do it. So that's actually motivated by this kind of a strategy. So now once you have this, you can use the exact same code and then just put it in, and you will get back this parallelized version that you can run with 8 machines or how many ever you want. So that has been toy example, 8 machines. But this exact framework actually works with any number of machines. And here I got it from the Google blog post. And this is actually what happens. So in TPU v4 pod, it can utilize like 3072 chips. And when we were training PaLM model, we used 2 pods. So it's like 6,000 chips showing here, each one being very as capable as some of the highest end GPUs. So now you have this bunch of machines you define a mesh, still the same thing. Model parallel dimension is 48, and data parallel dimension is shown in 2D, but you can flatten it out, and then you have a 64. In PaLM, we actually use different things, but actually this is exactly same. Same framework, just more machines. One last bit of detail is this DCN data parallelism. So when the two pods are really not connected in anything, but it's connected with the data center network, I think it's like 25 GPS per second. So this is slow compared to what's connecting the GPU pods. So here, we should not do any model parallelism. What we do is after the gradient computation, we sum the gradient over this data center network, and that's done only once, and that takes, say, 1 second or something. I don't know exact number, but this is fine because when we're training models like PaLM 540 billion, you can actually look at the paper. Each train step takes like 17 seconds. So if you add in like a 1 second here and there or 0.5, doesn't really matter. This is really different from small model training where we're thinking about steps per time. We're talking about seconds per step. So I think also it's really cool to just experience-wise, I type in some code and then enter in my laptop, and then it just runs on all these machines. That I think is really cool, and I think scaling, if you understand this, that what's happening at the end is just matrix multiplication with many, many machines that I just explained, you'll probably feel a lot better about this process. So far, we have assumed that this parallelized decorator just works. How is it actually done? One approach is this GSPMD. I linked the paper there, and it's a compiler-based approach. And you write neural net code as if you have a machine with infinite memory. So you don't really have to parallelize anything, which is kind of the approach we took. We just wrote no communication written, and then represent the core part of this neural net, say this train step, as a computation graph. And then you can just, the graph is defined by some input tensor coming in, output array going out, and so on. You just specify how those are mapped to the hardware axis. It's the same process with it, and give that to XLA. It automatically inserts all gather, any other communications that has to happen to use all that machine. And this is literally a magic when it works. It doesn't always work, and it really requires a lot of iterations, and many people struggle. Now I think it really works. And if you think about all the big models that came out of Google, T5, PaLM, Switch Transformer, all these things use GSPMD as a backend, exactly using the process I described. Other approaches exist. I'm not as familiar than this one, but you could think about manually annotating instead of doing the compiler, the operations. But at the end, the process is just the same. All involves mapping the array axes to hardwares. That's all. And manual approach is sometimes better because you have more control over. So I have some concrete examples. So this one is this process of doing GSPMD is too probably complicated for most researchers. So JAX exposes this front end called PJIT. I think now it's just called JIT because it just becomes a so useful thing. And just the process is we define this train step that has to be parallelized, and then we wrap this with JAX at PJIT, which is a decorator thing. You get back this partition train step that can run with many, many machines. And this exact code path actually was used to train PaLM. And so you can take a look how this kind of thing is actually done. It's a little bit more boilerplate, but now that you have this framework understanding, you can probably just have some ideas what's going on there. These codes are open source, and this is based on this T5X framework. We have very short paper illustrating the systems there. I linked it at the bottom there. So that's good. It's all about engineering hardware, system level thing. What about this machine learning picture? So here is a Llama 2 which recently came out. So all looks good after a successful run. But one critical thing when you're actually running pre-training is that it's really expensive to iterate on ideas. Maybe you want to do this kind of data split, or you want to do this. And each run has to be done at some scale, and that's really expensive. So this is the ideal picture. In reality, if you're running on this, so let's say this is a 2 trillion tokens, right? I don't know how long it took. So let's say it's 50 days. Then let's think about in one day what the progress looks like. It's like this. And you have to make decisions. Oh, looks like our 70 billion model is doing well. And that I don't think I can make that call. And this is already using one day of thousands of GPUs hogged up, and then you to do some experiment. This is very difficult. So and this is even a good case. And sometimes it's not really clear what to do. And making decisions with this many resources waiting for me is just quite stressful situation. So this brings to the fundamental thing in pre-training is all about scaling laws. And GPT-4 technical report has some ideas about this, and OpenAI has published scaling laws paper in the past. That I think is really critical concept. So here we're talking about prediction, extrapolation of the performance of the pre-trained model across orders of magnitudes. Like just GPT-4, this one is a prediction, and this scaling law is developed with small scale model. So now we can see, okay, if we were to scale up, then this might be what we get. And we kind of, this is like the test loss on the unseen corpus, but this is the guiding principle. And so this picture is a lot more satisfactory if you have underlying scaling laws. And this is really the critical part of the pre-training. So I would like to say that now scaling is like a lot easier than say 2 years ago, but still very hard. And it's just not going from some flag, small to large, because of the mentioned reasons. And maybe one example, in palm training, there were like loss spikes. This is actually from the papers, you can check it out. There were about 20 loss spikes that happened. And this really unnerves many people, like just loss spiking up from like 2 to 6. It's really looks not good. So we trained 3 models, exact same data, but only one of them had the largest one. And so it's hard to debug and really hard to reproduce this kind of thing at smaller scale. And this is not caused by bad data. Some researchers run this experiments to verify this hypothesis. And then when this happens, every hour we not making the decision is like having this giant 6144 chips sitting idle, and that's really hard. And so this kind of makes really scaling challenging. And also, but then Llama 2 and all these things make much easier to train for a given size, like tens of billions of model like Llama, it's easier to train. But I would say that scale is increasing at a faster rate than the rate at which things become easier. At the frontier of the frontier, it's always challenging for many reasons. But most people will be not scaling up. I think you can just wait for them to do the hard work, get it, and do interesting research on top of it. So that leads to this next section. Scaling doesn't solve all the problems. We also need to do a lot more research on top of this massive engineering work. And many of those can be framed into this post-training. So let me talk about some motivations why we might need post-training. We cannot talk directly to this pre-trained model because the learning objective was just next token prediction. So here's one example I put. Let's say the input was make up a word that means when 2 AI researchers go on a date, and then pre-trained model will just continue generating because it doesn't know that it has to answer the question. It just predict whatever is the most likely and just go on forever. And whereas what we want is more like this, just crisp answer. And this is kind of the language models that we know how they behave. So that's one problem. This one, we have a remedy, more like a hack. We can frame the question so that the answer happens to be the next token. So here's another question, it's a square root, whatever, some question, and then we give a colon. And then the model just doing the next prediction, now it's like answering this question is probably the most natural thing, so we just do it. If it doesn't, then we can put an example, a few examples with the answer so that it knows how to do the thing. This is the few-shot prompting. It is quite powerful technique, but it's not really general and probably not the most principled solution. So probably a bigger problem than this formatting error is that pre-trained models always generate something that is natural continuation of the prompts, even if the prompts are malicious, harmful, and so on. And in particular, it doesn't know how to refuse a prompt. And all these capabilities that we think are important is taught at the post-training level. Sometimes people call it alignment. to human values. I just call it post-training. Here, here's kind of the 4 stages of current generation of large language models. Pre-training is the first stage, and then there are 3 remaining stages: instruction fine-tuning, or sometimes people call it SFT, supervised fine-tuning, and then reward model and policy model training. That's kind of the RL part, RLHF. So we'll go in these 3 orders, 1, 2, 3. So let's take a look at the instruction fine-tuning. The high-level idea is that we frame all the tasks in the form of natural language instruction to natural language response mapping. So I think the best way to think about this is what we did before we had this idea. So if we go back to 2018, BERT was the best model at the time. And say we are solving this classification task. We just have, again, functional viewpoint. Input is the text, output is the label, classification label. To do this kind of task, we have to do BERT maps the sentence, and then you need to project to the classification space. We need a task-specific parameter. And this was not really fun to extend it out to multiple tasks. T5, a year after, came along with unification of the architectures, and that now the output is text. So you just map text to text. All the tasks look similar, same, and it's much better. But now if you're training on multiple tasks, multitask learning, then there's no way to distinguish the task. So you kind of put in this metadata. This is COLA task from Glue, and then some additional things for other tasks, so that at the inference time, if you prepend this, then the model knows that I'm solving this COLA task. But this is very unnatural. Instruction following goes one step further and explains the task in natural language. Is the following sentence acceptable? That's exactly what we mean by COLA task. We don't really need COLA. That's just some random data, and this is what we mean, and then explain the concept. And for the other task, we can also do the same thing, explain in natural language. The model understands and does the task. So this now looking back, this is so obvious. We should have done this. Why this was not obvious at the time of T5 2019, 2018 was that at the time, people did not really think that language models understand the instruction. So having this kind of metadata felt more natural, and even this was like a stretch. So now we have larger models where kind of the emergence is this understanding, which in a very vague sense is possible. This kind of utilizing the rich space of natural language makes all the things unified. So that's the viewpoint of net instruction following. And maybe one more generalization will be, instead of instruction in response out, you can think about dialogue as a kind of ultimate, most general form of 2 agents interacting, and some of them involve question answering or other things. So this is the instruction fine-tuning idea. So last year, when I was still at Google, I did work on this paper where we pushed the limit of instruction fine-tuning. Okay, so instruction, actually, let me just take one more thing. So if you train on these instructions, say you see a new task at the inference time, then the task is unseen during training, but still, this is just framed as a instruction. So you just follow that instruction. That's how the generalization is done. And I think it's really critical concept. So that means if we have more instructions in the training set, would that be a better model, better generalization happening? And that was the hypothesis we tested with this massive thing, tasks. So at the time, we gathered pretty much all the academic tasks we could find. Then there were like 1,836 of them, put it into one mixture, train it. I won't go into detail. I linked this paper at the bottom. And this is where like Flan T5 and Flan Palm, those models came out. And so here we have a model X size and the x-axis. Whenever we think about some idea, always plot the scaling so that we understand the effect of the scale on this research idea. 8 billion, 62 billion, 540 billion. And on the y-axis, some average score of the evaluation set. We carefully picked 6 of them unseen during training and very hard, as evidenced by this 8 billion palm model, which was trained well, but still getting less than 10%. So the takeaway is that as we go from this gray line to the darker and darker blue, we add more tasks and the performance monotonically increases, but with the diminishing return. And that is more probably clearly shown in this plot on the right, number of fine-tuning tasks on the right, and then same data point, but you see like each model gets the benefit of like 10%, but adding more tasks doesn't really help. So what matters is the task diversity. But still, even with this 1,800 tasks, massive benefits happen for any model size we have tried, any model family we have tried. And I think for this kind of method, it's hard to see any use cases that doesn't benefit from this. So very effective, but it has inherent limitations. Again, let's think about fundamental reasons why this might be not so scalable or effective. And for that, we need to go to the learning objective. In this learning phase, what are we teaching the model? And so learning objective, that is supervised learning with cross-entropy loss or maximum likelihood objective, which means for this given input, the target we have is the single correct answer, everything else is wrong. Very strong statement. In reinforcement learning literature, this is called the behavior cloning. I kind of like this terminology better. So the hope is that if we have enough of these variations, the model can generalize to different types, even though the training signal was quite prescriptive. So crucially, this requires formalizing the correct behavior for a given input so that the model can clone. And this has been easy and straightforward in the past. Increasingly, this is becoming more difficult. And the way I'm going to illustrate this is I'm going to show you a bunch of examples, and let's do a thought experiments where just think about the single correct answer. It has to be a single one. So start with the trivial example, 2 plus 3. Then it's obvious that the answer is 5. Maybe the answer is 5 might be a better one. But anyway, this one, not ambiguous. Another one, a little bit more ambiguity here. Translate this Korean. I should have studied instead of watching this movie. And this one, I translated myself. I know Korean, so this probably is correct. But this, but it's a single correct answer, but there might be some variations in it. Now, this is kind of the problems that we're actually dealing with in large language models. Write a letter to a 5-year-old boy from Santa Claus explaining that Santa Claus is not real, convey gently so as not to break his heart. And this one, I cannot think of any good answer, let alone the best one that I will confidently give it to the model and say, this is a single correct answer. So this kind of thing, I'm less confident and comfortable using this maximum likelihood as the learning objective for the largest model we have. And that's maybe a little concocted. So let's think about some more practical use cases. This is actually one of the favorite prompts that I use whenever there's a new model comes out. Implement logistic regression with gradient descent in Python. And for this one, there's no clean answer, single answer for this. You might like functional programming style, you might like object-oriented style, or you might, within that, your style might be different, and all those might be valid. So is it okay to give one of the completion as the only correct answer? So let's make some observations. Increasingly, we want to teach models more abstract and ambiguous behaviors. And objective function of the instruction fine-tuning seems to become the bottleneck. I don't have hard evidence. In practice, this generalizes quite well. But if we think about, say, 1,000 times larger model than GPT-4, are we comfortable teaching the model with this very narrow signal? At least I'm not. So then can we use something? What is this maximum likelihood objective? If I give you a model prediction and a target, then there's a predefined mathematical function that computes this loss or objective function. So there's no learnable parameter. If this is the bottleneck, can we make this more expressive and actually learn it and parameterize it? And that's kind of the key idea for the RLHF. And RL provides one of many ways of doing this using this learned objective function. So in RL, we try to maximize this expected reward function shown here. Very general formulation. So let's think about, say, an agent playing chess. At the end of the game, if it wins the game, we give the reward of 1, reward of 0 otherwise. This is a valid function we call a reward, but there's no learnable parameters or anything. But we can actually use a model to formulate the rewards for more complicated situations, and we call that a reward model. So from this perspective, how do we actually do that? We know how to do supervised learning with neural net very well. So let's use neural net to represent that reward model. And that brings it to the next stage of reward model. So the core idea here is that for a given input, we give two completions, and humans provide the preference instead of saying which one is the best answer. Among these two, this is better. The initial, like this kind of thing doesn't really say why, but this is better. And human labels, just this is how models learn what humans prefer. And this, crucially, the completion two in this case is preferred, but it doesn't have to be the best one. It's just better than the other one. Then the model can learn the axis of difference, and this is really critical behavior. And why is this? Why do we use comparison for things like this? 2 plus 3. The fact that 5 is better than 4 is probably not useful because there's a single correct answer. Why not use the supervised learning with maximum likelihood objective function? But for Santa Claus example like this, I can probably come up with two somewhat, just good completions, and then just say this one is better, and that might be better. So the core hypothesis is that it's easier to compare than to absolutely grade something. So mathematics of this, I will probably skip it, but we just model it. I'll go very quickly. Two completions, yi and yj, and call probability Pij is the probability that completion I is better than j. And we get that label from humans, and we model that probability as a difference in reward, more specifically log odds, but that's kind of the model from 1952. And this, we just rearrange it and maximize this probability because it's essentially a maximum likelihood. The reward model is trained with the maximum likelihood, just maximize this probability, but that's fine because it's going to be rich function providing the signal to the policy model, which is the final stage of this large language model. And here, the objective function is what we just learned, reward model with the parameter phi that is fixed after the initial RL. And you might this might remind you of the GAN formulation where you have this discriminative generator. Here, we were kind of fixing one part of it and just doing the other iteration. So for this, we bring some prompts. This policy model, which is typically initialized from the supervised instruction fine-tune checkpoint, you just generate some completions for that prompt, give it to the reward model, it gives back the score. And based on that, if it's low, then I know, okay, this is not good. If it's high, then okay, I will do more of these. So it's a trial and error formalization in mathematics. That's essentially the high-level idea. And because we want to maximize it with the gradient-based iterative method, we just take the gradient, hope to take the gradient, and that is done by some policy-graded algorithms like PPO or anything that should work. So that's the idea, iterate while satisfying this RM model. And in doing so, RM encodes human preference and then gives it to the policy model, learn through RL. That's the kind of the framework. In practice, many people don't like this. And I secretly hear people saying, oh, we should just get rid of the RLHF. And many people say that, not just like, I'm not talking about OpenAI in specific, but just many people in the field say that. So why is it? It's really hard to get this right. RL is just so tricky and it can go wrong. And one failure mode that is probably the most common I would like to explain is what's called reward hacking. So let's say the human labelers label this completions, like comparison pairs, that this is better with whatever they're thinking about. But it happens to be that, say, the preferred completions are all longer. Then this policy model can exploit this fact that, okay, if I just give something longer, then the reward model likes it. And increasingly, it just gives something like dumb but long. Then it can get better and better rewards. This reward model is happy, and human preference goes down. This divergence is what we call reward hacking, and so hard to control. I don't think there's a great answer to this at this point, open-ended research question. And this kind of thing is really a good problem to solve because I don't think we have used this RLHF any way. Like this is just scratching the surface. So yeah, that's the kind of the failure mode that is most common. And there are kind of many ways to do that, but I'll probably skip that for now. So even with this kind of a fundamental challenge that it's hard to use it, why should we keep studying RLHF? Here's just my take. Maximum likelihood is too strong of an inductive bias. And if we think about very strong inductive bias, it will be problematic if we have much larger scale. So GPT-4 probably fine, but 1,000 times GPT-4 or even larger, this I think will be problematic. So learning this objective function to relieve this bottleneck in the inductive bias in scaling is a different paradigm, and there's a lot of room for improvements. We have seen some success stories with RLHF model like ChatGPT, but I think it's just a beginning. Also, here's my just personal take. If something is so principled, we should just keep at it until it works. So I would like to summarize this kind of what I just said in the post-training section with bird's eye view of the field of AI progress, starting with this rule-based system, which I'm not really familiar with, so I might make mistakes, but just high-level concept matters here. Input is mapped by this hand-designed program to output, and here nothing is learned. And the next generation is like a classical machine learning system where input is transformed to hand-designed features, and then that gets mapped to an output by this learnable part that is, let's say, like an SVM or something. And this is the, I label learnable part with the blue box. And then the output is fed to along with the input, hand design loss function, objective function, and then iterate. So deep learning did change one thing. This is that hand design feature was changed to learn feature. In particular, hierarchical representation learning was the technique that defines deep learning. And this one change was really successful. And why is that? That is because it is a much weaker inductive bias, and that allows much more scalable system. And we have a lot more compute, utilize it, and that's how the deep learning success story can be summarized. So if we think about classical machine learning versus deep learning, the closest comparison will be logistic regression with the feed-forward neural net. Same thing, except for the fact that the representation, it has some hidden representation that is learned from the data, that is whatever the model thinks is a good thing to solve this binary classification task. So at this point, I was wondering what will be the next generation. If just changing, coloring one box with blue was so successful, why not do another thing? And I only see one box left over, which is this loss function. So this still is hand design. So maybe we should relieve that assumption and learn it. And that, I think, is the next generation. We have one or two success stories, GAN and RLHF. And this is, I think, really powerful. And it allows a model that demonstrate behaviors that is so hard to think about if you have to formalize the correct behavior. So, but it can be RLHF just one instance. It can be any other RL formulations or any types of other methods, not just RL. So that, I think, is the next paradigm, and we should go for that. And if I have to think about this mental picture, what is kind of the representative flagship model from each paradigm? Maybe like IBM Deep Blue. I don't know what exactly uses, like some search with that, but let's call it just robust system. And then I don't actually have a good idea of any famous classical machine learning system. Let's call it some SVM-based ones. And then from there to the next paradigm was GPT-3. So now this much change happens in every paradigm. And I believe that learning this loss function or objective function is as big of a change from the previous steps. Then I think it's really exciting to think about what can come out of this. That's it. Thank you.